Nite is, I would say, a great match for me. I'm a medical doctor. I'm doing a PhD in neurology. And that's how nerdy you can get if you're into medicine. In general, you have doctors who like to think. They go into internal medicine. You have doctors who like to do things and don't like to think that much. They become surgeons. And you have the nerds. And the nerds, they go into neurology. So I think tonight it's a great match for my resume. And yeah, you won't wonder that I will talk about the brain tonight. We all have a brain, and our brain puts us at risk for developing Alzheimer's disease. I think it's our most precious possession in daily life. It helps us to remember all the things we do in life. It helps us to communicate with our loved ones, but it also describes part of our behavior and makes us the human being we are today. And I think it's really difficult for human in general, but especially nerds, to lose all those abilities. And what I want to start with is to give you a brief walkthrough through the brain. And this is the brain. In red you can see the frontal lobe, so that's the front of the brain. And in green you can see the back of the brain. In blue is the temporal lobe. Temporal lobe is the lobe I'm using now to memorize the talk I'm giving to you. And that's done by the hippocampus. The hippocampus is the organ that's responsible for memory processing, so for learning new information, but also for recalling information. And as I'm standing here presenting, formulating sentences, I'm also using my frontal lobe, in red here, to formulate sentences. The frontal lobe is involved in initiative, but also in inhibition. And without my frontal lobe, with the nerve probably, I would run off the stage, but my frontal lobe inhibits that impulse, and I just keep on talking. So that's the frontal lobe, initiative, but also inhibition. And we wouldn't be as social as we are if we wouldn't have that frontal lobe. And that's what you can see sometimes in patients who suffer injury in the frontal lobe. Their character changes. The yellow lobe then is called the parietal lobe. And by a look in the audience, I can see that all your parietal lobes are functioning pretty good, as you managed to find the way to crea. And finding the way is a function that lies in the parietal lobe. Also, knowing left from right is a function of the parietal lobe. I couldn't find evidence that the parietal lobe is smaller in women. You might guess. Couldn't find any evidence. The occipital lobe is also a lobe you are using now, watching these slides, watching around you, is involved in visual processing. Light comes into the retina, is transmitted to the occipital lobe, and that forms an image that you see and can interpret. So that's a brief walkthrough to the brain. You might notice that I only pointed out higher order functions, so not moving and stuff, but also about thinking. And that's exactly the kind of functions that would decrease in diseases such as Alzheimer's disease. Alzheimer's disease is the leading cause of dementia. There are 45 million people affected by the disease. And with the increasing lifespan, we expect this figure to increase to 115 million. Large numbers, but yeah, what does it say? I think the number on the screen here speaks more to you. 1 in 8 will develop Alzheimer's disease. And if you look around you, we can fill a department of the nursery home with people being affected by Alzheimer's disease. Apart from the figures, it's a horrible disease, not only for the patient and themselves, but also for their surroundings. People often ask me, what is the difference between dementia and Alzheimer's disease? Well, a brief answer to that is that dementia is a syndrome. So it describes that you have problems in cognitive functioning, for example, memory, but it could also be language or behavior. And it's not just for a few days, but it's progressive in time, and it leads to dysfunction in daily living. So, for example, during work or tasks around the house. And there are several diseases that can cause a dementia, and the most frequent form of dementia is Alzheimer's disease. So 70% of dementia worldwide is Alzheimer's disease. The Alzheimer's Association is an American association trying to find a solution for Alzheimer's disease. And this is one of the latest infographics they published, and just wanted to show you a few of those figures just to highlight the essence of doing Alzheimer's disease research, because it's also a huge economic burden. Every 66 seconds, somebody in the US develops Alzheimer's disease. I also found this one interesting. Since 2000, deaths from heart disease have decreased by 14%, while deaths from Alzheimer's disease have increased by 89%. So you see a huge increase in Alzheimer's disease-related death. It's not that you die from Alzheimer's disease, you die with Alzheimer's disease. Well, it's good to realize in Alzheimer's disease research, if I'm able to use my clicker, that's also frontal lobe. Yeah, it's just one sentence, but yeah. What have we learned? It's good to realize that the Alzheimer's disease research field is decades behind on, for example, oncology, cardiovascular disease. There's like 50 to 80 years of research in those fields, and the research have shifted from understanding the disease to treating the disease. While in Alzheimer's disease, we're currently unraveling what's happening in the disease rather than finding a cure. Nevertheless, this is a slide describing the major findings in Alzheimer's disease research. Don't be scared, we won't go through it all. I will just point out the start of this graph. 1906, Alois Alzheimer was the first doctor to describe a patient with Alzheimer's disease. And under the microscope, he saw changes in the brain that he called amyloid plaques later on. And I'll talk about those plaques, the amyloid protein, later on during this talk. And it was until the 1990s that the research really boosted with the help of the MRI scan and later on the PET scan. So this shows that the research field is relatively new, but you can see a huge increase in research after the 1990s, 2000. So I think that should give hope for the future. What have we learned? Well, what we basically learned is what's the problem in Alzheimer's disease. I told about the clinical signs, so forgetting things. But what happens in the brain? It's a brain disease. And what happens in the brain starts years, actually decades before symptoms occur. And the first leading event is accumulation of the Alzheimer protein, also called amyloid, in the brain, and that leads to brain damage. You see if I can show you, yeah. Here in red is the amyloid plaque, and this is exactly the same thing as Alois Alzheimer described in 1906. What happens? This protein starts to accumulate, causes damage to the surrounding nerve cells, and those nerve cells die, and therefore the brain shrinks. And if the brain shrinks in certain regions of the brain, that will lead to dysfunction of those areas. Well, we'll walk through this frontal slide, as we call it, or coronal slide of the brain. So that's a slice like this. You see through it from front to back. This is the right side, this is left. Here you see the gray matter and the white matter connecting all the nerve cells. That's normal. You can rely on me here. And this is the hippocampus, so that's in the temporal cortex, and that's the organ that's used for memory processing. And here, this is a normal shape of the hippocampus. Rely on me again. And what happens due to this Alzheimer protein is that you will get damage in several lobes. The temporal lobe, the hippocampus, but also sometimes the parietal lobe. That's more often seen in young patients with Alzheimer's disease. And that causes, for the temporal cortex, for the hippocampus, causes memory complaints. But for example, for the parietal lobe, gives problems with finding the way or knowing left from right. So that's basically what happens. This is in short. It's far more complicated, but this is the basics. And what we have learned by studying the disease is how we can diagnose Alzheimer's disease as specific as Alois Alzheimer did in 1906. As a doctor, the situation is still the same. We tell somebody the problem is Alzheimer's disease, and as a doctor, we can't do anything about it, but at least we know for sure what the problem is. So that's bad news. We can agree on that, I guess. What we do, we perform neuropsychological evaluation in order to objectify if there are memory complaints, not only complaints but also disorders. And the second thing is to find proof for Alzheimer-related damage in the brain. And the first step is to perform an MRI scan where you can see brain shrinkage of, for example, the hippocampus. And the second step is to find this Alzheimer protein. There are two ways of doing that. You can perform a lumbopuncture where you get cerebrospinal fluid. That's the fluid that normally surrounds the brain. So when you hit your head against something, it's kind of an airbag, but it's not air, it's fluid in this case. And that fluid that can show what happens in the brain. And you can measure that exact protein in this fluid. The other option is to perform a PET scan, and there you can see where the actual protein is present in the brain. So that's what we can do now. And what's good to realize is that Alzheimer's disease is slowly progressive, so that Alzheimer protein starts to develop 10 to 20 years before symptom onset. It's not something you develop over a few weeks of time. It's something that develops in years. So just want to show you one scientific graph tonight. This is it. On the x-axis is cognitive functioning. And most of us will be on the left side here, I assume, as cognitively normal. And depending on where the Nite takes us, will translate a bit to the right. But at least we won't reach this part where it's dementia and you have problems in your daily abilities. And there's this phase in between. We won't go into depth, but the problem there is that you have cognitive disorders, but you're still able to do your daily routine. And on the y-axis, we see abnormality of the measures we take when we see a patient. So for example, the amyloid is in red here. We can ignore the blue one, but the green one is the MRI scan, so brain shrinkage. In purple is memory, and here's clinical function. So that's how you actually perform your daily tasks. And what's interesting here is that the amyloid starts to develop really early, way before there's brain damage, and then you will get memory problems and problems in daily functioning. So there's a huge window of opportunity here in which we can intervene. So that's the good news. It's not only bad news I'm about to bring, there's also good news, and I'm optimistic. So we need this good news to go on with the research. I think if you read newspapers or read online about Alzheimer's disease, this is basically what you get from research. And that's that a lot of the trials we conducted, or the field conducted, failed. And what we mean by fail is that we weren't able to retrieve people's memory. And I think if you look at the data, that's true. We were not able to do that. But there's also a slight hope here. There's light at the end of the tunnel. What we tried to do was wash away this Alzheimer protein with different therapeutics. And what the latest trials show is that we can actually do this. We can remove the Alzheimer protein from the brain. And this is a slide that shows that. Here is the brain of an Alzheimer's disease patient before we gave therapy. So the red means that there's amyloid. And after we treated the patient for a year, the Alzheimer protein is gone. Still, we weren't able to retrieve the memory. And I can show you why, I guess, by this slide. What I keep on saying we, but what the field did was administering medicine while people were already demented. So they already had the brain damage in their brain, that's why it's called brain damage. And we were able to remove the amyloid, but the brain damage was already done. So I guess what we need is intervention in this early stage where there's no severe brain damage. So we need to be able to identify those people at risk for Alzheimer's disease in order to prevent the brain damage causing the dementia. So what we basically need is a biomarker, so something we can measure, that is easy available, not too expensive, patient-friendly, and early in the disease course. And we feel like we have the idea that we can use the eye to overcome this problem. I told you that Alzheimer's disease is a brain disease, so why look in the eye? Well, the eye is derived from the neural tube, and that means that both these parts contain neurons. And those neurons might reflect, the retinal neurons might reflect what's going on inside the brain. And the easy thing about the eye is that you can easily look into the eye with the use of light. And therefore you might see if there's changes in the neurons that are located in the retina. So there are two questions we're asking in the research I'm conducting as we speak. And the two questions are, is there thinning of the retina? So if we know that there's shrinkage of the brain, is there also thinning of the retina by problems with the neurons present there? And the other question is, can we detect the Alzheimer protein? And the second step is, as I say, the most interesting of the two. What we use is something from your kitchen. Who knows the spice curcuma or curcumin, turmeric? Yeah, I think we all have eaten it. It's used in nasi, but also in Indian curries, and it's actually in this Dutch ice cream that I get. It's yeah, it's this part. This part, the orange part, is curcumin. Actually, it's used for the color. And what we know, turmeric is specifically binds to the Alzheimer protein and is fluorescent by nature. And those characteristics make it easy for optical imaging, or make it easy, but make it possible to detect the Alzheimer protein in the eye. That's what we're currently working on. So I just summed it up, so that's easy. We administer curcumin, so that's the active substance in turmeric, in capsules to patients. And then we do optical imaging of the retina in order to detect the fluorescent signal of the complex of amyloid and curcumin together, in order to detect Alzheimer-related pathology early in the disease course, non-invasively, patient-friendly, and inexpensive. And if we can come up with this solution of early diagnosis, the next step is to have a successful therapy, but at least you can start treating when there's no brain damage present at all, or just a bit. That's one of the projects the center I work is working on. We're also looking for subtypes of Alzheimer's disease, different measures of early diagnosis, and also therapy research. This was the part I wanted to show to you. Dirk pointed out that I was the one trying to solve the disease. What I want to emphasize tonight is that it's not only me, not only the medical field that can do this research, but we need everybody on board to end Alzheimer. There are different ways of doing that, just raising awareness for the research. For example, wearing these socks. Those two socks represent the problems you have in Alzheimer's disease, so you mix up your socks, and that can get a conversation going about Alzheimer's disease, and it's not just aging, but it's an actual disease. And if you haven't seen this movie, Still Alice, go see it. It's really informative about what the disease can do to a young woman in their 50s. So it's not only a disease for elderly, but also for younger people. And if you want to contribute by doing sports, you can join our team. This is the team from last year. We did the Damloop and we raised money and we raised awareness for Alzheimer's disease research. So if you're sporty and you're willing to join us, you're welcome. Thanks for your attention, and I'm happy to take questions.